All right, let's talk about the mechanical properties of fluids. Whether you're in full-on exam prep mode or you're just a little curious, this is going to be your 5-minute crash course to really nail down the big ideas.
So let's start with a puzzle. How in the world can a huge steel ship, which is obviously super dense, just float on calm water? And on the flip side, how does a massive airplane use moving air to fly? Well, the answer to both lies in the fascinating world of fluid physics, and that's exactly what we're going to unpack right now.
First up, we're diving into hydrostatics. It's a fancy word, but it just means the physics of fluids that aren't moving, fluids at rest. And we're going to start with the most fundamental idea of all: pressure.
Okay, to really get a handle on pressure deep down in a fluid, I want you to do a little thought experiment with me. Just picture an imaginary cylinder of that fluid, kind of like a cookie cutter shape, with a certain area A and a certain depth or height H.
So, think about it. What's pushing down on the bottom face of our little imaginary cylinder? It's just the weight of all the fluids stacked right on top of it. And that gives us our classic starting point from physics. Force equals mass times gravity, or F equals mg. Simple enough, right?
But we can take it one step further. We know that the mass of anything is just its density, that's the Greek letter rho you see there, times its volume. And what's the volume of our cylinder? Well, it's just the area of the base, A, times the height, h. So if we pop that into our force equation, we get force equals A times h times rho times g.
And here it is, the final step. Pressure, by definition, is just force spread out over an area. So if we take that new equation for force and divide it by the area A, you see what happens? The A's cancel out, and we're left with this beautiful, simple formula, P equals H rho g. This is huge. It means the pressure depends only on the depth, the fluid's density, and gravity. Not the shape of the container, not the total amount of water, just how deep you are. You absolutely need to remember this one.
Okay, we've looked at what happens deep inside a fluid. Now, let's come up for air and focus on what's happening right at the surface. This is where some really cool stuff like surface tension comes into play.
So, what is surface tension? You know, it's this amazing property that makes the top layer of a liquid act like it's a super thin, stretched out elastic sheet. It's the reason tiny insects can literally walk on water, and it's why soap bubbles pull themselves into a perfect sphere. That's the smallest possible surface area they can have.
And this idea of surface tension leads directly to another cool effect called capillary action. Just look at the forces at play here. You've got this upward pull from the surface tension clinging to the walls of a narrow tube, and that upward force is in a constant battle with the downward pull of gravity on the weight of the liquid itself.
The whole principle is really just a tug of war. For that column of liquid to be held up inside the tube, that upward force from the surface tension has to perfectly balance the downward force from the weight of the liquid it's lifting. It's all about equilibrium.
And when we do the math on that balancing act, we get this formula for the height of the capillary rise. Now don't get intimidated. H is the height, T is the surface tension, R is the radius of the tube, and the rest are our old friends, density, gravity, and the contact angle theta. But here's the key takeaway. The height H is inversely proportional to the radius R. In plain English, the skinnier the tube, the higher the liquid climbs. Definitely one for your exam toolkit.
Okay, enough with fluids sitting still. Let's get things moving. We're officially shifting gears from hydrostatics to hydrodynamics. It's time to talk about the power of flowing fluids. Take a look at this. We've got a fluid flowing through a pipe that gets narrower. Now, the big idea here is something called mass conservation. Basically, if the fluid can't be compressed, then the amount of it that flows into the wide end each second has to be the exact same amount that flows out of the narrow end. You can't create or destroy the fluid, right? What goes in must come out.
And that whole idea is wrapped up neatly in the equation of continuity. A1V1 equals A2V2. A is the area and V is the velocity. So if the area A gets smaller, the velocity V has to get bigger to keep things equal. It's that simple. Less space means more speed. You've seen this in action every time you put your thumb over the end of a garden hose to make the water spray out faster.
So we just saw that when a fluid speeds up, say in a narrow pipe, something has to change. But what about its pressure or its energy? To answer that, we need to bring out the big gun of fluid dynamics, Bernoulli's principle.
When you get right down to it, Bernoulli's principle is just a version of the work-energy theorem that's been customized for fluids. All it's saying is that if you do work on a chunk of fluid, that work is going to change its total energy, that is, its kinetic energy from moving and its potential energy from its height.
So, where does the work come from?
Well, it comes from the fluid pushing on itself, from differences in pressure. The net work done on a little volume of fluid as it moves is just the difference in pressure between where it started and where it ended, all multiplied by that little bit of volume.
And now we put it all together. We set the work done by the pressure equal to the change in kinetic energy plus the change in potential energy as our little fluid chunk moves along its path.
And after a bit of rearranging, we get this incredibly powerful and elegant equation, P plus 1/2 rho v squared plus rho gh equals a constant. Here's what that means in plain English. Along a streamline, if one part of the equation goes up, another part has to go down to keep the total constant. So, if the speed v goes up, the pressure P must come down. This is it. This is the core principle that generates the lift that makes airplanes fly.
Okay, for our last topic, let's talk about something that feels a lot like friction, but for fluids. It's a property called viscosity. We're going to see what happens when an object tries to fall through a fluid. Think of a marble dropping through a jar of honey.
You see, when an object falls through a fluid, it doesn't just accelerate forever. It eventually hits a maximum speed called terminal velocity. Here's the play-by-play. Gravity is pulling it down, for sure, but there are two upward forces pushing back, buoyancy and this drag force from the fluid's viscosity. And here's the key part. This viscous drag gets stronger the faster the object goes. So eventually, the object is moving fast enough that the total upward push from buoyancy and drag perfectly cancels out the downward pull of gravity. At that exact moment, the net force becomes zero, the object stops accelerating, and it continues to fall at that constant final speed.
Phew, that was a lightning-fast tour, I know. But to help you lock in all the essentials, we've boiled it all down and put the most important formulas you need onto one final summary slide.
And there you have it, the 5 big formulas we've talked about, all in one handy place. From pressure in still fluids to continuity and Bernoulli's for flowing fluids and everything in between. This is your key takeaway. Go ahead, pause, grab a screenshot. This is your new best friend for exam revision.
And I'll leave you with one last thing to chew on. Take another look at that big Bernoulli's equation. What do you think happens to it if the fluid isn't moving at all, if its velocity is zero? How does that connect back to the very first formula we talked about today? It's a great little puzzle that shows how all these concepts are really tied together. Thanks for joining me on this quick run-through, and good luck with your studies.